Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mayo, and I'll be helping moderate today's webinar, GPU Programming in Julia. In this webinar, we will cover the different Julia packages and programming models for working with GPUs. We'll explore Julia packages and tooling available to efficiently develop a GPU application or accelerate your existing code base. Our focus will be on NVIDIA hardware using CUDA software. We'd like to have this interactive session today, so please write your questions in the chat and we'll either address them on the fly or address each question individually following their demonstration. With that said, I'd like to introduce you to today's presenter, Dr. Tim Bassard. Tim is a software engineer at Julia Computing working on GPU support for the Julia language. He holds a PhD in computer science engineering from Ghent University in Belgium for research on abstractions to program hardware accelerators in high-level programming languages. Please welcome Dr. Tim Bassard.
Can you hear me okay? Eric?
Yeah, Tim, we can't hear you.
Okay, great.
Just need to turn up the volume a little bit there. Thank you.
Is this better?
Much better.
All right. Let me share my screen. Can you all see my screen? I guess so. All right. Welcome everybody to this webinar on GPU programming in Julia. This is the third iteration on this webinar. So if you've joined in the past, there won't be that much new content. Of course, the entire webinar has been updated to match new and changed APIs in CUDA.gl. And there's also some new slides on task-based concurrency, which is a new addition to CUDA.gl 3.0. Let me start with an overview of the outline of the next 40 to 45 minutes, I think. So we're going to start with a short introduction on why Julia, the programming language, is well suited for GPU programming. And then I'll explain how you use Julia with CUDA.gl, which is the package for programming NVIDIA GPUs. And the remainder of this webinar will then be specific to CUDA.gl, which means it's specific to NVIDIA GPUs. However, as you'll see, much of the stack and much of the things I'll explain are actually portable across backends. So the things you learn here, you'll also be able to use with Intel GPUs with the OneAPI stack, or with AMD GPUs and the AMD GPU.gl based stack. So let's start with a brief introduction on Julia, the programming language, which I'll assume is all familiar to you. Julia is well known for CPU programming, and it has a couple of very interesting features. So on one hand, it's a powerful high-level programming language, which gives you a lot of interesting features. On the other hand, we still retain great performance, as you can see on this small overview of some micro benchmarks that have been implemented in can you only now see my screen? I just saw a pop-up about Eric, is everything okay?
Yes, all good. We can see that.
Okay, thanks. Okay, so let's continue. Performance of Julia is great. So on this chart here, you see the performance compared to a couple of other popular languages. And the big advantage of having a language that's both high level and performs well is that you can solve the so-called two-language problem. So typically you have the performance-sensitive parts of your programming language, such as the linear algebra libraries and so on, implemented in a performance-oriented language like C, C++, Fortran, and so on. And then the application is implemented in high-level language. With Julia, it's possible to use the single language for everything because it's performing so well. And I'm happy to say that all that just carries over to GPU programming. So we still retain the powerful high-level language, but performance is great. So on this benchmark overview here, we see a couple of benchmarks from the Rodinia benchmarking suite, which is a popular parallel programming benchmark suite implemented in CUDA-C, and the performance of that compared to the same benchmark implemented in Julia using CUDA.gl. As you can see, performance is on par, so we can still retain the high performance that GPUs have to offer in CUDA C, but then with Julia. And as a result, we also solve the two-language programming problem of GPU programming. And you can use a single language, Julia, to work across your GPU application stack. So in Julia, it's possible to write or use applications that are written in Julia. For example, we have a package for climate modeling that supports GPU programming. We have an entire suite of differential equation solvers that are GPU compatible. You can do quantum computing with GPUs. And this small example here is using Flux, which is one of our most popular machine learning packages, where it's as easy as just instantiating your model, instantiating some parameters, putting both on the GPU by calling the GPU function, and then by evaluating your model using those inputs, you're effectively using the GPU to do machine learning. And all of that is made possible by the second level of the programming stack, which is array programming. So with arrays, it's easy to use GPUs because array abstractions, using an array to perform computations, map well onto the massive parallelism that a GPU has to offer. And all of our popular GPU packages, CUDA.gl, OneAPI.gl, AMD-GPU.gl, they offer a very easy to use array programming interface to work with their GPUs. And all of those interfaces are already fairly similar across backends. And that's because all of them are built on top of the GPU arrays.gl package, which gives a common base of GPU array functionality. What's in the name? And this example is something very typical. So you just load one of the GPU backends, you generate some data on the CPU, you can upload it to the GPU by calling the constructor of the array type, and then you can just conveniently execute operations like, for example, I'm broadcasting the sine function here, and then I'm taking the sum of the result. And all of that is going to execute on the GPU without having to know how to program a GPU. And that's because, again, the array programming interface maps well on the parallel hardware that the GPU has to offer. Of course, in some cases, you might have to go deeper and write your own kernel functions, as they are called. And again, all of these backends here, the AMD, the CUDA, and the Intel backend, they offer such kind of a kernel programming interface, which again is fairly similar across the backends because all of them are built on the same stack. They're using the GPU compiler.gl infrastructure package that creates a GPU compiler for all of these backends to use. And typically your kernels will look as follows, where you write a function that's execute in a scalar fashion, and to differentiate what you're computing, you need to compute or otherwise evaluate which thread you're currently executing for. And in the CUDA world, that's doing by the thread index function, which you see called here. With other backends, that function is called differently, but the principles stay the same. So as I mentioned, for the remainder of this webinar, I'm going to focus on the CUDA.gl package. But as I've shown in the previous slides, much of the principles are applicable to other backends too. To start using CUDA.gl, nowadays it's very easy. You just have to install Julia, obviously. Then you need an NVIDIA driver. But once you have the NVIDIA driver, it's as easy as installing the CUDA.gl package and importing the package. And all of the other dependencies, such as the CUDA toolkit or the cuDNN library, or in this case also the cuTensor library to accelerate specific tensor operations, all of that is going to be downloaded automatically. You can see that happen with the downloading artifact line that's being printed there when we perform an initial operation. And in this case, I'm calling the version info function, which is a convenient function to display some information about the detected setup. If you want, you can opt out of these automatic binaries being used by setting the Julia CUDA use binary builder environment variable to false, in which case CUDA.gl will try to detect all of these libraries as available on your system. But it's generally not recommended to do so because this is the configuration we test, for example, on our continuous integration service. And nowadays it's also supported for all major platforms. So unless you're on a very specific platform, there's no real reason to opt out of it. And if you don't have a GPU, and something that we definitely need to mention is that Julia Hub is nowadays one of the easiest ways to get started with Julia and GPU computing, because spinning up a machine with a GPU attached to is as easy as browsing to the Julia Hub web page and clicking the launch button. So I'm going to quickly illustrate that. If you just go to the juliahub.com webpage, you'll have to make an account. But once you do, you can navigate to the compute section of Julia Hub. And there you can launch applications. For example, you can launch the Julia IDE application, which if you do so, I already have launched one, but if you click the launch button for the first time, then you can easily select a GPU machine and get started in no time. Now, the cost of this in this case is $1.40 an hour, but if you're a first-time user of Julia Hub, you get some free credit. So this is really great to get started with GPU programming in Julia. And once you have that set up, you can just connect to your Julia IDE, which is powered by Visual Studio Code, by clicking the connect button. And I've done that over here. You just get dropped into a VS Code instance that looks very native. You can, for example, click the Start REPL button to get enter a REPL, and in here I've installed the Julia package as I've shown in my slide. You can import the package, do a version info as I mentioned, and you can see that you get a fairly reasonably powerful GPU to work with on an otherwise fully idle system. So again, with the free credit that there's to offer, this is a great way to start with GPU programming in Julia. Let's go back to my slides. All right, there we go. So to actually get started with programming, as I mentioned, arrays are a great way to do so. And in order to make everything familiar, we try to be as compatible with the base array type you're probably familiar with as possible. For example, these constructors are typical constructors that you'd expect to be able to call with an array type. You can initialize a undefined array with some dimensions. You can create a similar version of that array. You can pass it some CPU data as well, in which case that data gets uploaded to the GPU. And you can also go back by calling the array constructor on the QArray object, in which case you'll download data from the GPU back to the CPU. We also have some convenience constructors, which have to be prefixed by the CUDA module because they don't take an array type as an argument. For example, you can do CUDA.ones, similar to the ones function you have in base to allocate a GPU matrix filled with ones. We have the same with zeros, fill, rand. All of these are very familiar functions that are available to quickly get started with some data on the GPU. We also have a lot of common functionality, like, for example, creating a subarray with the view function. And of course, we also have a lot of common operations, not only storage on the GPU, but also computing things on the GPU, such as taking the sum of an array, multiplying an array by a value, doing a matrix vector multiplication, taking the adjoint, and so on. And again, all of this is meant to be as compatible with the base array type as possible. And whenever possible, we'll be dispatching these operations, for example, this multiplication of a matrix and array, with some high performance libraries behind the scenes. So these libraries are developed by NVIDIA, and as I mentioned, are automatically installed when you use CUDA.jl for the first time. And when you call certain operations, like, for example, initializing a GPU array with random numbers, then we'll be using the current library. We'll be using cuBLAST for a lot of linear algebra functionality, same for a lot of cuSolver functionality. If you call the FFT function, we'll be using cuFFT. Lots of functionality that's required for machine learning will be dispatching to cuDNN, and so on and so forth. So this makes sure that lots of operations execute with very high performance. But of course, real flexibility that we have in Julia are these so-called higher order abstractions. For example, the map function, where you can allocate an array A, as I do here, and then I take the map of this array, where I'll be doing an element-wise addition of every element with 1. And this is really powerful because we as library developers, we have implemented and optimized the map function, but we're really composing this function here with some code that's only part of your application. Nonetheless, everything as a whole is going to be compiled into a single specialized kernel, meaning you don't have to write kernels, but you can still use custom code on the GPU. We have a couple of these. For example, the map can be represented more succinctly by doing this dot operation, an element-wise addition. You can also call the reduce function, passing in an anonymous operator. Same with accumulate, same with find first. We have a bunch of these, and this gives you a very powerful array language where you can use these operators with your code without having to write custom kernels. And an added advantage of this is that all of these instructions, all of these operations here are really GPU agnostic. There's nothing in here that's GPU specific. They are all abstractions from the base array library, which means that you can create an application written using this powerful array language that's fully GPU agnostic, but nonetheless is GPU compatible by just switching the inputs from a CPU type to a GPU array type. And to illustrate that, I've got some codes that I copied from this course a while back, where some user implemented a small machine learning model. So there's a loss function that's defined, and the gradients of the loss function. We have a small training loop that uses proximal gradient descent, and all of this is executing on the CPU. Just by virtue of changing the inputs and the weights to a GPU array makes all of this execute on the GPU, and it even does so pretty fast, so performance isn't too bad. Of course, this is a best case scenario. I admit all of these operations happen to be implemented by the CUDA.jl package or the GPU arrays package. It's always possible that some operation isn't implemented properly or optimized for GPU execution. And something that then can happen is when, for example, this norm function from the linear algebra package, up until a couple of weeks ago, that wasn't implemented, wasn't specialized by the CUDA.jl package. And the result then is that we fell back to the generic implementation of a norm calculation in the base library. And the disadvantage of these fallback implementations is that they often iterate. So they take a single value from our array at a time, they do something with it, and then they store it back in memory. And this completely defeats the purpose of using a GPU, because it's just going to be transporting element by element from the GPU to the CPU and perform the operation there, completely ignoring all of the advantages that a GPU has. And as a result, this is a very slow operation. So I'm benchmarking both here. With a CPU array, it takes 3 microseconds. With this GPU quote-unquote implementation, it takes 10 milliseconds, which is much, much slower. And that's why we warn by default if you're triggering such kind of scalar operations. Of course, actually a warning may not be enough, and you can prohibit these operations from being called at all, which is something useful for doing, for example, your test suites, by calling the allow scalar function and passing false as the argument. So this may be a good reason to implement a custom kernel. Another good reason is that performance may not be ideal if you're, for example, calling several array operations that could otherwise be fused together. So for this contrived example, I'm taking an array with 10 million elements and I'm adding it to its reverse. And those are 2 individual operations. So we have first the reversal of the array, and then we have a element-wise addition. But the real question is this actually slow? And this is a good place to illustrate some of the tools we can use to measure this. So naively, you might just stick the @time macro in front of your GPU expression. And as you can see, it takes a very, very short period of time. And this is because this is wrong. And the reason being that most GPU operations are asynchronous, meaning if you execute the operation from the host, it's only going to queue the operation on the GPU. It's not going to wait for the GPU to finish. And that's because you can actually submit more operations and only wait when you require the results. And a typical waiting point is when you copy data back from the GPU to the CPU. So that means our time measurements here are wrong. And the way to work around that is by wrapping our expression in the CUDA.addSync macro, which is pretty similar to basis addSync macro. And the macro is going to synchronize the GPU, meaning it's going to actively wait until the GPU finishes executing our operation. And as you can see, the time spent is a lot longer. And to make this convenient, CUDA has its own addTime macro, which does the synchronization for you. And in addition, it also reports on GPU memory allocations. For example, here we see that we have 2 GPU allocations, which makes sense because one allocation is from the reversal and the other is from the output of the broadcast operation. Of course, you can always use the benchmark tools package with it at benchmark or at btime macro. Then you, of course, need to combine again with the addSync macro because benchmark tools doesn't know how to synchronize GPU. But on the flip side, you get some more accurate measurements. So it's recommended to use benchmark tools whenever possible. And just to compare this to the original CPU implementation, if we were to perform this reversal and element-wise addition on the CPU, you can see that we get a nice speed up by doing this contrived operation on the GPU. But this is pretty superficial in terms of profiling. We just get to see the time spent for the entire operation. And this is also where NVIDIA comes in with some great tools for, among other things, profiling the execution on the GPU. And this is a helpful overview, a helpful chart that NVIDIA has on their website where they explain which specific tool to use when you want to profile a GPU application. And basically, it's always start with Nsight Systems, because Nsight Systems will give you a nice overview of your application's performance and visualize it using a timeline. And as you'll see, that timeline is very valuable. Once you notice from that profile that a specific kernel is slow, you can always use Nsight Compute to do a deep dive on the performance of your kernel in question. So let me illustrate Nsight Systems. All of these tools are compatible with Julia and CUDA.gl, and we can profile anything done with CUDA.gl by just running it under the Nsys profile tool. For example, again, we import CUDA, we allocate our array. I've left this out for brevity, and then we do our operations. So again, the reversal and the element-wise addition. And as soon as we exit our application, we get a profiling report saved into a QDREP file. Another way of invoking Nsight Systems is by using Nsys Launch. And this has the advantage that we won't have to exit our Julia session, where we can just profile and revise our code interactively. In order for the Nsight System tools to generate a reporting file, we have to wrap our expression into the CUDA@profile macro, whereas otherwise Nsight Systems would have profiled our entire application. But again, we get an output file and we can use that output file with Nsys stats to see some superficial statistics about our kernels. But the most valuable thing to do is to use the Nsight System user interface. If we then load our report file, we get a very useful timeline of execution. And what we can see here is that both our kernels, so the reversal kernel and the broadcast, they happen one after one another, and the GPU is kept busy. And that's good, but it doesn't always happen that way. For example, if we profile a session where we do some very superficial operation, we might see this very sparse timeline where we have a couple of small blocks indicating GPU execution, but between that, the GPU is virtually idle. And this is a very bad way because it underutilizes your GPU by a lot. What you really want to do is to saturate the GPU, which is visualized on the timeline by a lot of these blocks being densely packed next to another. And some way to do this is by, for example, increasing the workload, processing more elements in your kernel, or making sure that the CPU isn't doing anything needlessly between individual GPU kernel launches. For more realistic applications, you might also want to enrich your profiler traces using NVTX. So NVTX is a library by NVIDIA, the NVIDIA tools extensions, and we have that wrapped in Julia and provides you a very useful at range macro that makes it possible to annotate slices of CPU computation, which get then visualized in the profiler trace. For example, here I've put some computations under the at range block called run one, and then we can see in our trace that this run one section is there with a useful timing next to it. And this is very useful for profiling more complicated applications or for figuring out where the latency comes from by gradually drilling down and adding more NVTX ranges to your applications. And this, of course, is even more powerful when you combine it with interactive profiling using the revise package. Insight System also supports multiple processes, multiple devices. So in this screenshot, this is a recent Julia application I was profiling where we were using distributed.jl, where every worker had its own specific GPU device. And as you can see, it's all visualized together neatly into a single timeline, which is very useful in figuring out why your GPU is not used efficiently. So this is the application timeline. If for some case some kernel turns out to be slow, you can use NVIDIA Insight Compute to analyze only that kernel. So you get rid of the timeline and you just zoom in onto a specific kernel. And the way to do this using CUDA.jl is similar. You launch Julia under NV Insight CU CLI. If you exit your application, you get a bunch of statistics. But once more, the more powerful way of doing so is by using Insight Compute's launch mode, in which case you can, again, profile interactively. And in this case, you don't get a report file. You have to do so by attaching the user interface to this running process. And all of that is explained in great detail in the CUDA.jl documentation. So if you ever need this, refer to the documentation. But just to show you what the user interface could look like, in this case, we can analyze the kernel and we can see a bunch of architectural specifics about that kernel, which is, again, very useful with interactive profiling, because then you can fine-tune your implementation and see if, for example, the cycle count went down or some other performance metric improved. So to go back to the original reason we were looking at this, our application, which did a reversal and then an element-wise addition, both kernels take quite a bit to execute. Whereas if we fuse them together, we might imagine that the application, that the kernel that does both operations at the same time would execute a lot faster. So let's give this a try by implementing our own kernel that performs this operation in one go. So naively, you might write a kernel that takes its own thread ID, as I mentioned before, and then computes the addition of the array with its reversal by calling the reverse function inside of a kernel. But if you were to do this, you'd get a nasty error when you launch the kernel complaining that this kernel function is not GPU compatible. And the reason behind that is that we cannot be compatible with certain operations that rely on the Julia C runtime library. And this call to reverse happens to allocate an array. And in this case, dynamic allocations and garbage collection in general are not supported on the GPU right now, because as I mentioned, they rely on Julia's C runtime library. We also do not support dynamic dispatch, which means that your kernels will always need to be tightly typed. And we also do not support input or output, for example, writing to the terminal or writing to files and so on. Luckily, this reversal is an easy operation to just do ourselves by indexing at the end of our array B. Again, let's launch this kernel on our 10 million items that we have. And now we get a CUDA error. And that's because we're violating some of the limits that the CUDA programming framework imposes on us, namely that the device we're working with can only launch 1024 threads at the same time. And all this is just to illustrate that CUDA.jl's kernel programming API doesn't do any magical for you. You still need to stick by the rules that the CUDA programming framework imposes on you. For example, in this case, we cannot launch as many threads as we want. We need to decompose our computation in terms of a number of blocks that each launch a number of threads. And we can do so easily by changing our index calculation to one that takes our block count into account. And then when we launch the kernel, we, instead of launching 10 million threads, we only launch 1024, and we compute how many blocks of 1024 threads we need to fully cover the length of our array. If we compare the performance of that to a CPU implementation, we see we get a nice speed up. Actually, I'm not comparing to the CPU implementation, I'm comparing to the previous GPU implementation where I was using multiple kernels. Now, just limiting the amount of threads you're launching to 1024 is not great, because in that way you're tying yourself to the device you're currently working with. Generally, it's recommended to use, in this case, the launch configuration API, which uses the occupancy API from the CUDA toolkit. And this is to illustrate that we offer the same flexibility and APIs that the CUDA programming framework has to offer, but typically we repackage it in a slightly more higher level API. For example, here, to query the occupancy API, you launch your kernel with the launch equal false keyword, which means it's not going to actually launch it, it'll just compile the kernel and give you a callable kernel object. And then you can use that kernel object to introspect, for example, the amount of threads and blocks you should ideally launch for this function and for your device. And then we can use that by calling the kernel function, passing the thread and block count as keyword arguments. But this is a general thing we do all the time in CUDA.jl. We take the CUDA APIs, we retain the flexibility, but we try to repackage it slightly to get the benefits from a high-level programming language. For example, thread indexing and block indexing is pretty identical, except that we're using a named tuple instead of a structure. You can use cooperative groups or dynamic parallelism by passing the appropriate keyword arguments to the @CUDA macro. We support shared memory, we support atomics, but again, many of these are slightly more higher level because us benefiting from the advantages that Julia has to offer. For example, instead of you having to call a bunch of atomic functions, we had to have this @atomic macro, which inspects the operation you want to do and automatically dispatches to an appropriate low-level atomic. Basically, that doesn't raise the abstraction level though. So you still need to know how to program GPUs at the abstraction level that you would have done in CUDA-C, but we just try to make it a little easier when you do so in CUDA.jl. That also means that a lot of the performance optimizations are similar. So you need to avoid thread divergence. You need to make sure that you reduce global memory accesses and that you coalesce those accesses whenever possible. You need to improve occupancy, for example, by using the occupancy API, as I've shown before. All of that is very similar as you would have done in CUDA-C. We do have a couple of Julia-specific performance recommendations, though. For example, Julia is a garbage collected language, meaning that when a GPU array isn't used anymore, it might take a while before the garbage collector picks it up. And if you're using an application that uses all of the GPU's memory, it may be advantageous to inform the CUDA memory allocator that this memory is ready to reuse by calling the unsafe free function, essentially bypassing the garbage collector, or at least not having to wait until the garbage collector comes by. For kernel programming, one thing you will want to do is avoid exception branches, because we make it a little more safer to program kernels. For example, we do bounce checking, we do checks for conversions from int to float and vice versa. Of course, when you do so in code where you know these errors can't occur, you might be paying a performance penalty that's not necessary. And typically, you avoid that in the case of bounce checks by annotating your code with the @inbounds macro. A similar thing to be wary about is that in CUDA C, all integers and floating point values by default are 32 bits, while in Julia, they typically are 64 bits. And GPUs, or at least consumer GPUs, don't perform that well when using 64-bit values. So one way to inspect all of this is to use the reflection tools that we offer you. So similarly to the code LLVM and other macros that you have in base to inspect the code that the base compiler generates for the CPU, you can use these @device code LLVM macros to inspect code generated by the GPU compiler. For example, here I'm taking our reverse kernel that we've developed. I'm sticking the @device code LLVM macro in front, visualizes or at least prints to the terminal all of the LLVM intermediate representation that was generated. And this isn't limited to just putting it in front of an @CUDA expression. You can also put it in front of an entire application, and then you'll see the code generated for all kernels that are being executed. We can also do so for the PTX code, which is the virtual ISA that's being used. Then we can see some lower level assembly code that may be very useful for optimizing specific kernels, because this is also the code that's being shown in NVIDIA tools. But we can even go one level below that by using the code SAS macro. SAS stands for shader assembly. And then you get to see all of the machine-specific code that's being generated by the NVIDIA assembler. But all of these are just for expert programmers who want to optimize their code. But they are also valuable for debugging compilation failures. For example, if I write this kernel here, and I've made a silly typo. Instead of thread IDX, I'm using the thread ID function. However, if we execute this, the GPU doesn't like this, and we get an invalid IR error. And we get to see a dynamic function invocation error, which is something that's not supported by our current GPU compilers. So oftentimes these dynamic function invocations stem from badly typed code. And a good way to debug that is by inspecting the generated typed code by putting device code warrant type in front of your invocation. And what we see here is very clearly that the thread ID call immediately returns any, and as such, it's also annotated in red. And that should ring a bell that there might have been a typo in your source code. Nowadays, CUDA.jl also warns you about some of these typos if it can spot them, but generally when you spot an any in the warrant type code, something's wrong with the function that you're calling. So if we fix this, then we get neatly typed code which executes properly on the GPU. So next to these tools that we have on the Julia side, NVIDIA also has a bunch of tools that you can use. Typically, these are useful when you have a kernel that executes but computes the wrong values. For example, I have a reversal kernel here that uses dynamic shared memory to efficiently reverse values from an array. However, I've conveniently commented out this synchronization call, which is necessary to correctly compute this operation. If we were to execute this, then we get the wrong result. And one way to debug that is by using the compute sanitizer by NVIDIA, which has a couple of modes. And the mode that I want to illustrate here is the race check mode, which is going to check for memory races. And that's something that's happening here because of the missing synchronization. And again, we can just launch Julia under this compute sanitizer tool, and it will report on the race that it detected between those two reads and writes from shared memory. And the compute sanitizer has a couple of other modes. It also has a memory checker, it has an initialization checker, it has a synchronization checker. For example, when you see an illegal memory access, it's always useful to run your code under the compute sanitizer using the memcheck tool. Now for some more advanced CUDA programming elements. Users who are familiar with CUDA programming might want to instantiate some more low-level objects themselves. For example, you might need access to the device object, to the context, or allocate your own buffers. And for most of these common operations, we have these high-level wrappers. So by just, for example, calling the CUDevice constructor, passing a device number, you get a neat device object you can introspect and call many other functions on. Same for context, the same for example, events for time measurements and so on. So these are high-level wrappers that make it much more convenient to work with the CUDA APIs in Julia. However, sometimes you might need something for which we haven't created such a high-level wrapper. Luckily, in that case, we actually give you the entire C API as well. So the CUDA module gives you access to the entire CUDA driver C API. And all of that is also compatible with the high-level objects. For example, this high-level context object here, I can pass it to low-level C API functions that require a CUContext pointer. And all of the conversions will happen automatically. And that gives you uncompromising access to the CUDA APIs, which means that if you need a certain feature that we haven't properly wrapped, like in this case, enabling peer-to-peer access between different GPUs, you can just use so, which makes it much easier to port existing applications from C or C++ to Julia. However, it is recommended to use the more high-level features when they're available. And even for these high-level wrapped elements, you might not necessarily need to use the CUDA APIs because CUDA.gl manages a lot for you. For example, instead of creating contexts and devices, it might just be okay to use the global device and context that CUDA.gl manages for you. Same with memory buffers. Most users won't actually need a memory buffer because you can just use the CUArray type to hold any memory you want. Similarly, events are typically used for time measurements, but we already provide the CUDA.addElapsed macro, which makes it possible to do fine-grained timing measurements using events. And finally, streams, which are typically used to perform multiple independent operations in parallel, you can avoid having to use your own streams by just wrapping GPU computation in Julia tasks. Because CUDA.gl is going to manage streams for you, and if it detects that operations are being issued from different Julia tasks, then it will automatically use a different stream, and that both for kernels and for library operations. For example, here I have a compute function that performs a matrix multiplication using cuBLAS, but it also does a broadcast, which uses a native Julia function, and then it synchronizes. And as you can see here, I'm launching this compute function from two different tasks, and in the timeline, we can clearly see that the execution of both instances are overlapping. And this is a great way to extend the utilization of your GPU when, for example, the workload of your individual kernels is fairly low. And this also extends using multiple devices. So every task can use its own device. Here I'm using two different GPUs from two tasks, and the execution is again overlapping. And it also extends to multiple threads, each of which can also use a different device. Of course, there's some caveats, there's some recommendations. And for that, I recommend you take a look at my JuliaCon talk on CUDA.gl 3.0, which is the version of CUDA.gl that introduced this feature. And this talk goes into a great detail on how you most appropriately use tasks to program GPUs concurrently. However, we're at the almost 45-minute mark, so I'm going to end here. Maybe in summary, so Julia is a great programming language for working across all the levels of a GPU application. So on the one hand, you can work with arrays, which is much easier because you don't need to write your own kernels. And at the same time, it also makes it possible to write generic code that executes both on the CPU and on the GPU. However, if necessary, you can always use CUDA.gl to write your own kernels with the same performance as well as flexibility that CUDA-C has to offer. And to facilitate all that, we have a bunch of powerful tools both for novices and expert GPU programmers that should make this all possible and easy. And for more info on all this, you can have a look at the CUDA.gl documentation, which is hosted on the CUDA.gl repository on GitHub. We also have a julia.gpu org site for everything on the different Julia GPU backends that we currently have. And of note there is that every couple of weeks to months, we publish a blog post, for example, on every new CUDA.gl release, highlighting the new features that this release has to offer. And if you have questions, of course, feel free to ask them on Discourse, on the Julia Discourse, or drop by Slack, where we have a GPU channel. All right, thanks for your attention. And I think now it's time for some questions and Q&A.
Tim, I don't see any in the chat. I know that we were on with a customer the other day, looking in the area of pharmaceuticals with biostatistics and Fisher-Pittman permutation analysis. I know that's kind of specific, but what are some of the areas that you're finding folks leveraging GPUs in industry, if you will?
Yeah, that's a tough one. And I'm not sure whether I'm in the best position to answer that question, because yeah, typically I'm confined to working on the compiler and the abstractions that people need, whereas the application level development happens slightly higher up the stack. For example, if you look at the diff-EQ stack, that's where most users will get into touch when using GPUs. And you typically only have to dip down into using CUDA.gl when there's missing functionality. And as such, most users are using GPUs without having to deal with CUDA.gl and without having to deal with me or getting in touch with how to improve Julia's support for GPU computing. Nonetheless, on the juliacomputing.com webpage, there's a GPU subsection, if I'm not mistaken, which has an overview of a couple of case studies. And of course, one of the most important ones of which is the entire climate modeling thing that's currently happening by Caltech and JPL and so on. So if you have a look at the climate.gl package, which is based on the oceananigans.gl package, there we have a lot of climate modeling that's actively using CUDA.gl, executing on supercomputers all over the US. So that's a definite one of the more bigger users of our stack. But beyond that, there's also a thread on Discourse where we recently asked all of our users to give us some details on what they were using the Julia GPU stack for. So if you're interested in that, I suggest you have a look at that thread, and then you can get some inspiration on what people are using our infrastructure for.
Awesome, Tim. Thank you. There is one question. I don't know if you want to read that one from Alessandro. And I'll address Peter Crosby's question in a minute as we close up, but essentially the one from Alessandro.
Yes, so the question that is, our team has a very substantial amount of code written for parallel use on CPUs. What approach would you suggest for porting on GPU? It depends what kind of a parallel API or framework you were using in the first place to execute in a parallel fashion on the CPU. Now, for example, if you were using one of the libraries like Trust, or maybe one of the Julia packages like distributed arrays that gives you a array abstractions executing in parallel, then this will be fairly easy to port to the GPU, because we aim to give you a similar parallelized array programming interface. Of course, if you had written code that, for example, was OpenMP style, where you had a lot of scalar kernels, then it's going to take a bit more effort to port. Luckily, we also have a couple of packages that facilitate this, and namely make it possible to retain the portability of scalar code between CPUs and GPUs, one of which is kernel abstractions.gl, which is a package where you can write these OpenMP style scalar kernels and at the same time have them compile for the GPU using, for example, CUDA.gl or AMD GPU.gl, or to the CPU and use multi-threaded CPU execution using Julia threads. So if you were to re-implement these scalar codes and you want to retain the ability to execute them on the CPU as well, then I recommend you look into that. But generally, when porting code, we recommend users, if they have to start from scratch, to have a look at the array interfaces, because much of the application will be able to be implemented using these kinds of abstractions, and you automatically benefit, or as a benefit, you get execution on both the CPU, the GPU, and whatever platform comes next. Or maybe another detail to mention is that traditionally, Julia also has a very powerful FFI, a foreign function interface, which means that it's very feasible to do this kind of port gradually. Because at the CUDA side as well, we interface with CUDA in a way that's compatible with existing CUDA applications. It's again feasible to, for example, retain most of your C or C++ or Fortran application, put it in a shared library, and then call it from Julia, or do it the way around and incrementally port code to the higher level language. Just passing memory from one language to another, even if it's GPU memory, should just work out of the box and makes it much easier to incrementally introduce Julia even for GPU computing in a complex application.
Looks like there's a question here from Peter.
Yeah, I'll read it. So the question is, are there random number generators available suitable for large-scale simulations on the GPU? And if so, are there examples of this sort of applications somewhere? We actually, so on the one hand, of course, you have Courant, which is a very high quality random number generator implemented by NVIDIA, but it has two problems. So on the one hand, it's limited in the amount of types that it supports, because it's ultimately a C library. And if, for example, you want to generate double float or int 128 or some other obscure type that we're used to using in Julia, with Courant, that's going to break down. And on the other hand, it's also fairly complicated to use Courant within a kernel. And that's why with CUDA.jl 3.0, we've also introduced a device-side random number generator. And we've used that to implement a much more generic host-side generator as well. So yes, with CUDA.jl 3.0, the ability to generate random numbers both in kernels and from the host has greatly improved. I recommend you also have a look at the CUDA.jl 3.0 talk I mentioned a couple of slides earlier, because there is a bit on the random number generators on there. Also on the respective blog posts on juliagpu.org. There was also a sub-question, is the 32-bit issue a problem? In this sort of application, I can't remember the last time I didn't use 64-bit variables. The reason it may be a problem, so for most scientific use cases, you generally want to be using 64-bit integers anyway, because the data sizes are getting so large that it is realistic that you actually overflow, for example, your 32-bit integer indices. However, recent Volta era GPUs have the ability to execute int32 operations together with certain floating point operations. And because we don't use int32 indices, we don't get to benefit from that. And basically, one of the advantages there is if you have indexing heavy codes, you can be computing your next index in parallel to the current one you're evaluating, presumably that pointing to some floating point value in an array. And that can sometimes result in a slight diminished performance, but I haven't seen it happen with the codes I have looked at. Nonetheless, it's something to keep in mind. If you really want to micro-optimize a kernel and squeeze all of the performance out of it, it might be beneficial if you're using a recent GPU to use 32-bit indices so that the GPU can execute floating point operations as well as integer operations concurrently.
Awesome, Tim. Thank you so much for answering the questions from the audience here. And thanks everyone for your participation. Once again, thanks Tim for your time and the excellent presentation. For Peter and for other folks interested in the recording of this presentation and our past webinars, you can visit the resources tab at juliacomputing.com. Once again, that's the resources tab at juliacomputing.com. For any help with your existing Julia use case or upcoming Julia project and GPU project, please reach out to us at sales@juliacomputing.com, and we'll be happy to help you. Thanks again, everyone, and have a great weekend.